Look up at the night sky for a moment. Not with a telescope, not with equations, just with the quiet feeling that something vast is above you. The moon seems to hang there with perfect patience. The stars seem fixed in their ancient places. The darkness between them feels empty, calm, and certain. And for most of human history, this is how reality has felt to us. Solid, stable, waiting. Whether we look at the moon or not, we assume it is still there. Whether we turn away from a mountain, a tree, or the hand resting beside us, we assume it keeps all of its properties, its shape, its position, its color, its quiet place in the world. This belief is so natural that we almost never notice it. It is the invisible floor beneath ordinary life. It is the feeling that the universe exists independently of us, carrying its truth whether anyone is watching or not. Albert Einstein believed this deeply. He did not believe the universe had to be simple. He had spent his life showing that it was not simple at all. He showed that time can slow down. He showed that space can curve. He showed that gravity is not just a force pulling objects downward, but the bending of the very stage on which everything moves. Einstein gave humanity a universe far stranger than the one we had inherited. And yet, beneath all that strangeness, he still believed reality should be real. He believed the moon should remain the moon, even when no eye was turned toward it. He believed objects should carry their properties with them, quietly and faithfully. He believed that nature might be mysterious, but it should not be vague at its foundation. There was another belief he held just as strongly. Nothing should influence something far away instantly. If one object affects another, something must travel between them. A signal, a push, a wave, a ray of light. Even light, the fastest messenger in the universe, still needs time. Sunlight takes about 8 minutes to reach Earth. The light from the nearest stars takes years. The light from distant galaxies travels for millions, sometimes billions of years before touching our telescopes. Distance matters. Time matters. No message should leap across the universe in no time at all. To Einstein, this was not just a technical rule. It was part of the dignity of the cosmos. The universe could be deep. It could be curved. It could bend time and stretch space. But it should not allow hidden whispers to pass instantly between distant things. It should not behave like a dream. Yet this is only part of the story. Because while Einstein was reshaping space and time, another kind of physics was quietly growing in the shadows. It did not begin with galaxies or planets. It began with the smallest pieces of reality: particles of light, electrons, atoms, tiny things, so small that ordinary language begins to fail around them. At first, quantum physics seemed like a strange but useful tool. It helped explain why atoms shine with certain colors. It helped explain how matter holds together. It helped explain the quiet architecture beneath everything we touch. But slowly, it began to say something much more unsettling. It suggested that the smallest parts of the world do not always carry fixed answers before they are measured. A particle might not have a definite state waiting inside it. Instead, it might exist in a kind of delicate cloud of possibilities. Not one answer, not another, but many possible answers held together in silence until an interaction draws one of them into the open. This was not the kind of mystery Einstein loved. Einstein loved mysteries that could be solved by finding deeper order. He loved the feeling that beneath confusion there was a hidden clarity. But quantum physics seemed to suggest that uncertainty was not just a weakness in our knowledge. It might be part of reality itself. That thought disturbed him, not because he lacked imagination, but because he understood the stakes. If particles do not have definite properties before they are measured, then the world is not quite the solid place we think it is. And if two particles can be linked across great distances in ways that appear to ignore ordinary space, then the universe is not quite as separate as it seems. Einstein could not accept this easily. He felt that something must be missing, some deeper layer, some hidden mechanism, some quiet instruction beneath the strange behavior. He was not trying to destroy quantum physics. He knew it worked. Its predictions were too successful to ignore, but he wondered whether it was incomplete. A powerful map, perhaps, but not the final map. A description of what we observe, but not a full explanation of what is truly there. This disagreement would become one of the most profound scientific debates of the 20th century. Not because it was loud, not because it involved explosions or spacecraft or distant planets, but because it asked something more intimate. What does it mean for something to be real? Does the universe have definite properties when nobody is looking? Can distant objects remain completely separate? Or is reality, at its deepest level, woven together in a way our everyday minds were never built to picture? For decades, this question seemed almost impossible to answer. Einstein could argue from one side. Quantum physicists could argue from the other. Both could use mathematics. Both could use logic. Both could point to experiments that seemed to support their view. But no one yet knew how to ask the universe directly. No one knew how to turn this quiet philosophical tension into a clean physical test. And then, long after Einstein first raised his objection, a path began to appear. A path that would lead from thought experiments to real laboratories, from chalkboards to beams of light, from the calm certainty of the moon to the strange behavior of particles born together in darkness. And eventually, it would lead to a Nobel Prize. Not for proving that the universe is broken, but for revealing that our ordinary picture of reality was never complete. To understand why, we must travel deeper. We must leave behind the world of chairs, mountains, and moons. We must follow two tiny particles of light as they separate from one another. And we must ask whether, even across the darkness of space, they remain connected in a way Einstein hoped nature would never allow. Before we follow those two particles into the dark, we need to understand the two quiet rules they were about to challenge. These rules are so familiar that they do not feel like scientific ideas at all. They feel like common sense. They feel like the way existence has to be. The first rule says that things are real. Not real in a poetic sense. Not real because we believe in them, but real in the simple, ordinary way. A thing has its properties whether anyone checks them or not. A stone has a shape before you pick it up. A closed book has a number of pages before you open it. A star has its light, its heat, and its motion, even while it is hidden beyond the clouds. This is the world we are used to, a world made of objects that carry their own facts. The facts may be unknown to us. They may be difficult to measure. They may be far away, buried, or hidden in darkness. But we assume they are there, waiting. This idea feels almost too obvious to question. When you leave a room, you do not imagine that the furniture dissolves into possibility behind you. When you close your eyes, you do not imagine that the world loses its form. When the moon sets beneath the horizon, you do not think it has stopped being the moon. You simply understand that it has moved out of sight. It remains itself. That is what physicists often mean when they speak of realism. The world has definite properties, independent of observation. Your looking does not create those properties. Your looking only reveals them. Einstein felt this deeply. For him, science was not just a collection of predictions. It was a search for what is truly there. A good theory should not only tell us what number will appear on a measuring device. It should help us understand the hidden order beneath that number. It should point toward a reality that exists whether or not a human being happens to notice it. This is why quantum physics troubled him. It seemed to work beautifully. It could predict the behavior of atoms with astonishing accuracy. It could explain the colors of light, the structure of matter, and the strange stability of the microscopic world. But when physicists asked what was happening before measurement, the answer became misty. A particle did not seem to carry one definite answer in advance. Instead, it appeared to hold several possible answers at once. Only when measured did one answer become real to us. To some physicists, this was simply how nature behaved. To Einstein, it felt incomplete. He could accept that our knowledge was uncertain. He could not accept that reality itself might be undecided. There is a great difference between not knowing the answer and there being no answer yet. If a coin is hidden under a cup, you may not know whether it is heads or tails, but you assume it is already one of them. Your ignorance does not create the result. You only discover it when you lift the cup. Quantum physics seemed to suggest something stranger. Before the measurement, the coin may not be simply heads or tails. It may be described by a blend of possibilities. Not because we are careless, not because our instruments are weak, but because, at the deepest level, the question may not have a fixed answer until nature is forced to give one. This was the first rule under pressure, the rule that things are real before they are observed. The second rule was just as important to Einstein. It says that the universe is local. Local means that events do not reach across space instantly. If one thing changes another, the influence must travel. It must cross the distance between them. It must move through space in some physical way. A sound travels through air. A ripple travels across water. A radio signal travels outward at the speed of light. A gravitational change travels through space-time. Everything we know about the large universe seems to respect this idea. Nothing simply appears everywhere at once. There is always a journey. There is always a delay. Even light, the fastest thing we know how to describe, still obeys distance. When you see the sun, you are not seeing it as it is right now. You are seeing it as it was about 8 minutes ago. If the sun could vanish in this instant, Earth would not know immediately. For 8 quiet minutes, daylight would still arrive. Warmth would still touch the atmosphere. Shadows would still fall across the ground. Only after the last sunlight had crossed the space between us would the news reach Earth. The universe does not deliver information instantly. It sends it across distance with patience. The same is true on cosmic scales. When we look at the stars, we are looking into the past. Some stars shine from hundreds of years ago. Some galaxies shine from millions of years ago. The most distant light we can detect began its journey before Earth existed in its present form. The night sky is not a picture of the universe as it is now. It is a memory field, a quiet archive of light arriving late. This delay is not a flaw. It is part of the structure of reality. It protects cause and effect. It keeps events in order. It prevents the universe from becoming a place where information can leap without crossing the distance between things. Einstein's theory of relativity made this rule sacred. Nothing that carries usable information can outrun light. No message, no signal, no command, no whisper from one side of space to the other. For Einstein, this was not merely a speed limit. It was a way of preserving the deep order of the cosmos. If something happens here, and something else responds over there, the connection must have a path. There must be a bridge through space and time. There must be a physical story connecting cause to effect. This is the meaning of locality. The universe may be vast, but it should not allow distant things to act like they are secretly one object, without anything passing between them. And yet, quantum physics began to describe pairs of particles that seemed to resist this separation. They could be created together, then allowed to move apart. One could travel to the left, the other could travel to the right. They could be separated by a room, a city, or in principle, by the width of the galaxy. And still, when measured, their results appeared connected, not merely similar, not merely arranged in a simple pattern, but correlated in a way that seemed stronger than any ordinary hidden plan should allow. This is where the calm floor of common sense begins to shift. If the particles had definite answers inside them from the beginning, then realism could survive. If a signal passed between them after measurement, then locality might survive, though only if the signal moved no faster than light. But quantum physics seemed to suggest something more difficult. The particles did not carry fixed answers before measurement, and yet their answers were linked across distance. This was the combination that Einstein found unacceptable. It was not just that nature was random. Randomness alone was not the deepest problem. It was not just that measurements were strange. Strangeness alone could still be studied. The real problem was that quantum physics seemed to place pressure on both of Einstein's quiet rules at once. Reality might not be definite before measurement, and distant things might not be as separate as space makes them appear. For a mind like Einstein's, this was too much to leave untouched. He wanted to know whether the strange predictions of quantum theory were truly revealing the nature of reality, or whether they were only showing the limits of the theory. Maybe the particles did have definite properties all along. Maybe there were hidden variables, hidden instructions, hidden facts carried quietly from the moment the particles were born. If those hidden facts existed, then the mystery would soften. The particles would not be deciding anything at the moment of measurement. They would only be revealing what had already been written inside them. The universe would remain real. The universe would remain local. And the strange fog of quantum physics would become a sign that we had not yet found the deeper layer. This possibility mattered. It gave Einstein a way to resist the unsettling picture without rejecting the success of quantum physics itself. He could say that the theory worked, but that it was not complete. He could say that the mathematics predicted what we would see, but not what truly existed beneath the act of seeing. He could say that reality still had a hidden foundation. A deeper foundation. A foundation that would one day restore the solid world. But the universe has another surprise waiting, because the question would not remain a matter of opinion forever. The debate would not stay trapped in letters, lectures, and thought experiments. The two rules, realism and locality, would eventually be placed under a kind of cosmic pressure, a pressure created by pairs of particles that seem to know one another too well. To understand that pressure, we must now move from Einstein's quiet principles to the strange bond that made those principles tremble. We must follow two particles born from the same event. We must let them drift apart, and then we must watch what happens when the universe is asked to choose. Imagine a tiny flash of light in the darkness. Not a sunrise, not a star. Only a single event, almost too small for the mind to hold. From that event, two particles are born, two photons, two little pieces of light. One moves one way, the other moves the opposite way. At first, they are close together. Then space begins to open between them. A few inches, a few feet, a room, a laboratory, a city, and in thought, if not yet in practice, the distance can grow without end. One particle could be imagined drifting toward Earth. The other could be imagined traveling toward a distant star. They would be separated by darkness, by time, by all the quiet emptiness that seems to make objects independent. And yet quantum physics says something remarkable about certain pairs like this. It says they may not be fully separate. Even after they move apart, they can remain described by one shared state, not two private stories, not two ordinary objects carrying two independent sets of facts, but one connected system stretched across space. This is called entanglement. The word sounds delicate, almost gentle, like threads crossing in the dark. But the idea behind it is one of the most unusual in all of science. When two particles are entangled, measuring one of them tells us something about the other. Not because we have opened two ordinary boxes with pre-written answers inside, not because one particle sends a normal message to the other, but because the pair seems to behave as if its deepest description belongs to both particles together. The whole comes before the parts. To feel why this is strange, picture two ordinary coins. You place one coin in one box and another coin in a second box. Before sealing them, someone arranges them so that one is heads and the other is tails. Then you send one box far away, maybe across the room, maybe across a continent, maybe, in imagination, to the moon. When you open your box and see heads, you instantly know the other box contains tails. But nothing mysterious has happened. The answer was fixed from the start. The coins carried their facts with them. You learned something about the distant coin, but you did not change it. You simply uncovered a secret that was already there. This is the kind of explanation Einstein would have found natural. It preserves realism. It preserves locality. The coins are real because each one already has its face. The coins are local because no influence needs to travel between them when the boxes are opened. All the connection was created earlier, at the moment they were prepared. But entangled particles are not like ordinary coins. At least, not if quantum physics is telling the full story. Before measurement, each particle does not seem to carry one definite answer waiting inside. Its possible outcomes are held in a kind of suspended balance, a quiet field of maybes. When one particle is measured, a result appears. And when the other particle is measured, its result is linked with the first in a pattern that is too strong to explain by ordinary hidden instructions. This is where the mystery deepens. Each individual result may look random. You cannot control what answer your particle gives. You cannot choose it in advance. You cannot use it to spell out a message. But when many pairs are measured, and the results are compared later, the pattern between them is unmistakable. The particles answer as though they belong to one shared reality, even when distance says they should not. The deeper we look, the stranger things become, because entanglement does not merely say that particles are similar. It says that the properties we assign to one particle may not be fully defined until the act of measurement. And yet, when that measurement happens, the distant partner is found to match the first, in precisely the way quantum theory predicts. It is as if the two particles are not two isolated objects hiding two separate answers. They are more like two ends of one quiet question. A question spread across space. A question the universe answers only when we interact with it. This is the point where ordinary imagination begins to lose its footing. We are used to thinking in objects. A stone here, a tree there, a planet circling a star, a galaxy far beyond our own. Each thing appears to have its own boundary, its own place, its own private existence. Space seems to separate them. Distance seems to protect them from one another. But at the quantum level, separation may not mean what we think it means. Two particles can be far apart in ordinary space and still belong to a single mathematical description. Their connection is not like a wire. It is not like a radio signal. It is not like a beam traveling from one to the other. It is something quieter and harder to picture. A relationship written into the state of the pair itself. This is why Einstein found entanglement so troubling. He was not confused by the mathematics. He understood it very well. What disturbed him was the picture of reality the mathematics seemed to suggest. If the particles had no definite properties before measurement, then realism was in danger. If their results were linked across distance without any normal signal passing between them, then locality was in danger. And if both things were true, then the ordinary world we trust would not be fundamental. It would be a surface, a calm appearance, a large-scale pattern emerging from a deeper world that is not built from separate, definite things in the way we imagine. Still, Einstein believed there had to be another way to understand it. Perhaps the particles did carry hidden answers. Perhaps each photon left its source with a complete set of instructions. Perhaps the apparent randomness was only a sign that we could not see the deeper order. In that picture, entanglement would not be mysterious at all. It would be like the two boxes with coins. The particles would have agreed on their behavior from the beginning. They would separate, travel through space, and later reveal answers that were already quietly written inside them. No instant connection would be needed. No distant influence. No violation of the cosmic speed limit. Reality would remain real. Reality would remain local. And the strange fog of quantum physics would be only fog in our understanding, not fog in the universe itself. For a time, this possibility could not be ruled out. It sounded reasonable. It sounded almost comforting. After all, science has often moved from confusion to clarity by discovering hidden causes. The motions of planets once seemed mysterious. Then gravity gave them order. The colors of light once seemed mysterious. Then atoms and energy levels gave them order. Why should quantum behavior be different? Why should the deepest layer of nature give up definite answers altogether? Einstein suspected it would not. He suspected that quantum theory, successful as it was, had stopped too soon. It told us the odds. It told us what we would measure. It did not tell us what was truly happening when nobody was measuring. This was the quiet heart of the disagreement. Not whether quantum physics worked. It did work. Not whether the equations were useful. They were among the most useful equations ever written. The question was whether the equations were complete, whether they described reality itself, or only the strange rules by which reality appears to us when we ask it questions. And that leads us to an even more fascinating question. How could anyone tell the difference? If hidden instructions were too small to see, how could scientists ever know whether they existed? If the particles only revealed their answers during measurement, how could we prove they had no answers before? For many years, this seemed like a question beyond experiment. A question for philosophers. A question for late-night conversations between brilliant minds. A question that could be argued forever and never settled. But Einstein did not leave the matter alone. In 1935, with Boris Podolsky and Nathan Rosen, he shaped his discomfort into one of the most famous challenges in modern physics. It was not an experiment made of metal and glass. It was a thought experiment, a carefully built trap, a way of saying that if quantum physics was right, then nature must accept a kind of connection Einstein believed no reasonable universe should allow. The trap would become known by three initials, EPR. And it would force physics to face the question directly. Either the particles carried hidden facts from the beginning, or something about reality was stranger than space, distance, and common sense had led us to believe. Einstein's challenge began with a simple instinct. If quantum physics seemed to make reality uncertain, then perhaps the theory was not showing the final layer of nature. Perhaps it was only showing the surface. Perhaps beneath the probabilities, Beneath the measurements, beneath the strange fog of possible answers, there was still a deeper order waiting to be found. This was not a small disagreement. It was not a matter of personality. It was a question about what science should be trying to describe. Should physics only predict what we will observe? Or should it also tell us what exists when no observation is being made? Einstein believed the second answer mattered. He believed physics should reach toward reality itself, not merely the appearance of reality, not merely the numbers on a screen, but the hidden structure behind those numbers. And so, in 1935, he joined with two younger physicists, Boris Podolsky and Nathan Rosen, to write a short paper that would echo across the rest of the century. Their argument became known by their initials, EPR, Einstein. Podolsky, Rosen. The paper did not use machines. It did not depend on a laboratory. It was a thought experiment, built from logic, a quiet test made of reasoning. And like many of Einstein's most famous ideas, it asked us to imagine a situation so clearly that nature would seem forced to answer. Begin with two particles. Let them interact. Let them become linked. Then allow them to fly apart. One particle travels in one direction. The other travels in the opposite direction. Soon, they are far enough apart that no ordinary signal could pass quickly between them. Not without taking time. Not without crossing space. Not without respecting the limit set by light. Now imagine measuring the first particle. According to quantum physics, that measurement gives you a definite result. And because the two particles were connected, the result also allows you to know something about the second particle far away. Here was Einstein's concern. If you can know something definite about the distant particle without touching it, without disturbing it, and without sending any signal to it, then perhaps that property must have already existed. It must have been there before the measurement. It must have been carried by the particle all along. If that is true, then quantum physics did not create the result. It only failed to describe the hidden fact that was already present. This was the heart of the EPR argument. Einstein and his collaborators were not saying that quantum physics was useless. They were saying it might be incomplete. A theory can be powerful and incomplete at the same time. A map can guide travelers across a continent and still leave out the deep tunnels beneath the mountains. A clock can tell time accurately and still hide the gears that make it move. Quantum physics could be a magnificent tool, but perhaps it did not yet show the hidden mechanism behind reality. To Einstein, this was the reasonable position. If the distant particle truly had a property that could be known without being disturbed, then that property belonged to the particle. It was not born at the moment someone looked. It was real. And if no signal had crossed the distance between the two particles, then locality was preserved. The universe remained orderly. No ghostly influence had to move faster than light. No mysterious connection had to ignore space. The particles had simply carried their instructions from the beginning. Like two sealed letters written at the same desk, then mailed to opposite sides of the world. When one letter is opened, you may immediately know what the other says. But nothing has traveled between them. The secret was written before the journey began. This image felt natural. It felt safe. It felt like the kind of universe Einstein could accept. A universe where the strangeness came from our ignorance, not from nature itself. A universe where every particle carried a deeper truth, even if our instruments could not yet read it. But quantum physics was moving in a different direction. Niels Bohr, Einstein's great intellectual opponent, did not accept the EPR argument in the way Einstein hoped. Bohr believed the experiment revealed something profound, but not that quantum theory was incomplete. To Bohr, the mistake was assuming that a particle must have definite properties separate from the act of measurement. The entire experimental arrangement mattered. The question asked of nature mattered. The measuring device mattered. The interaction mattered. In Bohr's view, we cannot simply imagine a particle carrying a complete private reality, untouched by the way we choose to measure it. At the quantum level, what can be said about a particle is inseparable from how it is brought into contact with the world. This was a difficult idea. It still is. Einstein wanted clear objects with clear properties. Bohr offered a universe in which properties do not stand alone in quite that way. A universe where the answer is not merely uncovered. It is formed through the meeting between system and measurement. Neither man was careless. Neither man was confused. They were looking at the same mathematics and seeing two different pictures of what it meant. Einstein saw a sign that the theory had not gone deep enough. Bohr saw a sign that our old idea of reality had reached its limit. For years, the debate continued. In letters, in papers, in conversations at conferences, in stories that physicists would later retell almost like legends. Einstein would present a challenge. Bohr would answer. Einstein would sharpen the challenge. Bohr would find another way through it. Each man carried a different vision of the world. Einstein's universe was strange, but intelligible beneath the strangeness. Bohr's universe was stranger still, asking us to give up the comfort of definite properties before measurement. And for a long time, there was no final referee. No experiment could yet decide between them. The predictions of quantum physics worked. The hidden variable picture could still seem possible, and the deepest question remained suspended. Maybe nature was truly indefinite until measured. Maybe nature only appeared indefinite because a deeper layer was hidden from us. Both pictures could survive in the imagination. Both could be defended. Both could be made to sound reasonable. This is why the EPR paper was so important. It did not end the debate. It clarified the wound. It showed exactly where the pain in quantum physics was located. The question was no longer only whether particles behaved strangely. They did. The question was whether that strangeness meant reality itself was not built the way we thought. Could the universe preserve both of Einstein's quiet rules? Could it remain real and local at the same time? Or would one of those rules eventually have to give way? For nearly 30 years, this question drifted. Einstein died in 1955, still dissatisfied with the quantum picture. Bohr died a few years later, still convinced that quantum physics had revealed something essential about the limits of classical thought. The argument outlived them both. It waited in the background of physics, not forgotten, not solved, waiting for someone to find a way to turn philosophy into experiment. And that is where the story takes its next quiet turn. Because far from the famous debates, far from the old conference rooms where Einstein and Bohr had argued, another physicist began to ask a sharper question. He did not ask whether hidden variables felt reasonable. He did not ask whether quantum physics felt strange. He asked whether the two pictures would ever make different predictions. Would a universe with hidden instructions behave exactly like a quantum universe? Or would there be a small difference? A fingerprint, a measurable trace, a number that could be counted. If such a number existed, then the old debate would no longer be a matter of taste. It would no longer depend on which picture felt more natural. It could be tested. The universe itself could be asked. And quietly, in 1964, John Bell found the question that Einstein had not lived to see. He found a way to draw a line between the world Einstein wanted and the world quantum physics seemed to describe. A line made not of opinion, but of mathematics. A line that experiments could cross. And once that line existed, reality could no longer hide behind interpretation forever. John Bell was not trying to make the universe more mysterious. In a quiet way, He was trying to make the mystery honest. For decades, the question had remained suspended between two visions of reality. On one side was Einstein's hope. The world was real. The world was local. Particles carried hidden facts, even if our theories could not yet see them. On the other side was the quantum picture. Particles did not always have definite properties before measurement, and entangled particles behaved as though distance did not fully separate them. The problem was that both pictures could be described in words. Both could be defended. Both could feel persuasive, depending on what one was willing to accept. Bell wanted something more solid than persuasion. He wanted to know whether a universe with hidden instructions would leave a measurable trace, a tiny boundary, a limit, a place where ordinary local reality could go no further. If such a limit existed, then the old question could finally be brought down from the clouds. It could be placed on a table. It could be counted. It could be tested by light, detectors, and patient machines. Bell's insight was gentle in appearance, but enormous in consequence. He realized that if particles truly carried hidden answers from the beginning, then those answers would have to follow certain rules. They would be like instructions printed before the particles separated. Measure this way, give this result. Measure that way, give that result. The instructions could be very clever. They could be hidden. They could be far more subtle than anything we could open and read directly. But if they were local, they could not know what distant measuring device would be chosen at the last moment. And they could not receive a faster-than-light message telling them how to respond. So Bell asked a simple question with a deep edge. How often could two distant particles agree if they were only following local hidden instructions? Not once, not twice, but over many trials, over thousands of pairs, over long lists of measurements. The answer, he found, was that there would be a ceiling, a maximum level of correlation, a line that no locally real universe could cross. If Einstein's picture was right, the particles could behave strangely, but only up to that line. Their hidden instructions could create patterns. They could create strong relationships. They could appear mysterious for a while. But in the end, the numbers would remain beneath Bell's boundary. Quantum physics predicted something different. It predicted that entangled particles would cross the boundary, not by a mistake, not by a little noise in the equipment, but by the deep structure of the theory itself. If quantum physics was right, the particles would agree in ways that no local hidden instruction system could reproduce. They would rise above the ceiling. They would step beyond the line, and that line would become one of the most important lines ever drawn in science. Not a line across a page of a map, not a line between countries, not a line marking the edge of an ocean. A line between two possible realities. On one side, the world could remain both real and local in Einstein's sense. On the other side, at least one of those comforts had to be surrendered. This is what made Bell's work so powerful. He did not prove quantum physics by asking people to believe in strangeness. He did not ask anyone to choose Bohr over Einstein by taste or temperament. He showed that the universe itself could give a score, a number, and the number would decide which kind of world we lived in. To understand the feeling of Bell's test, imagine two distant observers. Each one receives one particle from an entangled pair. Each one has a measuring device. Each device can be set in different ways. Each setting is like asking the particle a slightly different question. The particle gives one of two possible answers: yes or no, up or down, pass or fail, light or dark. The words do not matter. What matters is the pattern. After many pairs have been measured, the observers bring their lists together. They compare the answers. They ask how often the results matched or differed, in just the way the experiment predicted. If the world is governed by local hidden instructions, Bell showed that the correlations must remain within a certain range. If quantum physics is right, the correlations can exceed that range. There is something beautiful about the simplicity of this. The question sounds almost impossible. Is reality definite before measurement? Can distant things be fully separate? Is nature hiding deeper instructions beneath quantum uncertainty? These sound like questions too large for a laboratory. Questions for philosophers under a night sky. Questions that might drift forever without landing. And yet Bell found a way to let small flashes of light answer them. He turned an argument about reality into an experiment about correlations. He turned a century's unease into something a machine could record. This is why Bell's theorem still feels almost miraculous. It does not remove the mystery. It gives the mystery a shape. It says that if the world is ordinary in Einstein's sense, then nature must stay within this boundary. And if nature crosses it, then the ordinary picture cannot be the final one. For years, Bell's idea sat quietly, too quietly. Many physicists were not eager to return to the old debate. Quantum mechanics worked. It helped build lasers. It helped explain atoms. It helped make possible the electronics that would eventually fill the modern world. The practical successes were everywhere. The philosophical discomfort could be set aside. There was work to do. There were calculations to make. There were instruments to build. As long as the theory predicted the results, many scientists felt no urgent need to ask what the results meant. But Bell had shown that meaning could no longer be dismissed as only philosophy. There was now a difference between the pictures, a physical difference, a measurable difference. And somewhere, someone would eventually have to build the machine. That person would not need to solve the entire mystery of quantum mechanics. He would only need to ask nature one very careful question. Do the particles stay below Bell's line, or do they cross it? Still, the experiment would not be easy. The particles would be delicate. The measurements would be faint. The detectors would miss some signals. The world outside the lab would be full of noise, stray light, electrical disturbances, imperfect equipment. Small errors that could blur the answer. The experiment would require patience. It would require stubbornness. It would require someone willing to spend years chasing a question that many people considered already settled or not worth asking. And that is part of what makes the next step in the story so human. Because the first person to carry Bell's idea into a real laboratory did not begin by wanting quantum weirdness to win. He was not trying to defeat Einstein. He admired Einstein. He wanted the solid, local world to survive. He wanted the hidden instructions to be there. He wanted Bell's line to hold. His name was John Clauser. And in the early 1970s, he began preparing an experiment that would take the old debate out of memory and place it inside a dark laboratory where single particles of light could be counted one by one. The scene was not grand. There was no giant observatory, no rocket launch, no shining machine floating above Earth, only a careful arrangement of light, filters, and detectors. Only a quiet room where the deepest question about reality would be asked in the language of tiny flashes. It is easy to imagine the patience of it, the slow gathering of results, the hum of equipment, the dim glow of instruments, the feeling that somewhere inside the numbers, the universe was beginning to speak. And Bell's line waited there like a horizon. If the results stayed beneath it, Einstein's hope could live on. If they crossed it, then the hidden instruction world would begin to fade. The particles would be telling us that the deeper layer of reality was not the one common sense expected. Yet this is only part of the story. Because a mathematical line, however elegant, is not enough by itself. Someone had to meet that line with an experiment. Someone had to create entangled particles, send them toward distant detectors, choose how to measure them, and count the fragile correlations with enough care to trust the answer. And so the story moves from Bell's quiet mathematics to a real machine. From a theorem written on paper to light moving through glass. From a question that had haunted Einstein to a set of numbers rising slowly in a laboratory. There, in the patient work of John Clauser and those who followed him, the universe would finally be asked whether Einstein's reality could remain whole. The first step toward answering Bell's question did not happen beneath a famous dome or inside a grand observatory. It happened in a much quieter place. A laboratory filled with careful instruments, fragile light, and the patience of people willing to listen to nature one photon at a time. John Clauser had read Bell's work and understood what it offered. Here was a way to test whether the universe could be both real and local in the old, comforting sense. Here was a way to ask whether hidden instructions could explain the strange behavior of entangled particles. And because Clauser admired Einstein's view, he did not walk into the experiment hoping to overthrow it. He hoped the line would hold. He hoped the numbers would stay on Einstein's side. This detail matters. It gives the story a human softness. Clauser was not trying to make reality stranger. He was trying to see whether the strange picture could be avoided. If entangled particles stayed beneath Bell's boundary, then perhaps Einstein's deeper order was still waiting beneath quantum uncertainty. Perhaps the particles really did carry hidden facts from the moment they were born. Perhaps the universe was still solid underneath the fog. But to find out, Clauser needed to turn Bell's delicate idea into an actual experiment. That meant creating pairs of entangled particles. It meant sending them in different directions. It meant measuring them with carefully chosen settings. It meant counting their answers, again and again, until the pattern became clear. The particles he would use were photons, particles of light, tiny messengers that can move through space with the quiet speed of the universe itself. To create them, Clauser and his collaborator Stuart Friedman used excited calcium atoms. When prepared in the right way, a calcium atom can release two photons in a linked pair, two small flashes of light, born from the same event. One traveling one way, one traveling the other. These were not bright beams that filled the room. They were faint and delicate, individual pieces of light that had to be caught by sensitive detectors. The work was slow. The signal was weak. The equipment had to be aligned with care. A slight imperfection could blur the result. A small source of noise could hide the pattern. But this was the nature of the question. To ask whether reality itself was locally real, one had to begin with something almost impossibly small. A glow from calcium, a pair of photons, a detector waiting in the dark. Each photon traveled toward a measuring device. Each device asked a question about the photon's state. Not always the same question. Different settings allowed the experimenters to build the pattern Bell had described. Over many trials, the results could be compared. The important thing was not a single measurement. A single photon pair could never reveal the whole truth. The important thing was the rhythm that emerged across many pairs, the quiet statistics, the hidden music of correlations. If the photons were only carrying local hidden instructions, their correlations would remain beneath Bell's line. If quantum physics was right, they would rise above it. For a long time, the experiment was simply work, adjusting, testing, waiting, counting. The drama did not come with thunder. It came with numbers. Small numbers gathered into larger ones. Patterns slowly becoming visible. The universe does not always answer in bright signs. Sometimes it answers through a column of data that grows quietly, while machines hum in the background. And when Clauser and Friedman finally compared the results to Bell's boundary, the answer was clear. The photons had crossed the line. Their correlations were stronger than any local hidden instruction picture could allow. Einstein's preferred kind of reality had not survived the test. The result did not say that Einstein was wrong about everything. Far from it. His theory of relativity still stood as one of the great achievements of human thought. His understanding of light, gravity, space, and time still shaped the modern view of the cosmos. But on this particular question, the question of whether reality could be both local and definite in the old sense, the experiment leaned against him. The particles did not behave like sealed letters carrying fixed instructions. They behaved like something stranger, something more deeply connected, something that could not be explained by ordinary local realism. It is worth pausing here, not to rush past the meaning, not to turn it into a slogan, but to feel the quiet weight of it. A young physicist had built an experiment partly to see whether Einstein's hope could be saved. And the experiment gave the answer that Einstein had resisted. Nature did not stay beneath Bell's line. It crossed it. Yet this is only part of the story, because science does not stop at the first beautiful result. It asks how secure the result is. It asks what might have been missed. It asks whether some hidden weakness in the experiment could still allow another explanation. Clauser's experiment was a turning point, but it was not the final word. There were still small openings, loopholes, places where someone determined to defend local realism might say that the result, though powerful, was not completely sealed. One concern was that the detectors did not catch every photon. No detector is perfect. Some particles were missed, and if enough particles were missed, one could imagine a subtle bias in the sample that was actually recorded. Perhaps, a skeptic might say, the photons that were detected were not fully representative of all the photons that were created. Perhaps the missing ones would have restored the result to Einstein's side. This was not the most natural explanation. But science takes such possibilities seriously. A narrow door is still a door. Another concern involved timing. If the measurement settings were chosen too early, or if the detectors were not far enough apart, then perhaps some ordinary signal could pass between parts of the experiment. Perhaps one side could somehow influence the other without breaking the speed limit of light. Again, this was not what quantum physics required. But a careful test had to make even this escape route difficult. If two particles are to challenge locality, the experiment must make sure there is no time for a normal message to travel between the measuring stations. The questions must be chosen late. The distance must be large enough. The timing must be sharp enough. The universe must not be given room to whisper by ordinary means. This is where Alain Aspect enters the story. A French physicist who understood that Bell's question had not merely been asked once. It needed to be asked more tightly, more cleanly, with less room for the old worldview to hide. Aspect focused especially on the timing problem. If the measuring devices had their settings fixed too early, then a skeptic could imagine that the particles, or some hidden mechanism, had somehow adjusted to those settings in advance. So Aspect designed an experiment in which the measurement settings could change while the photons were already in flight. This was the essential idea. Do not let the particles know the question too soon. Let them leave their source. Let them travel outward. Then, at the last possible moment, change the way they will be measured. The timing had to be so fast that no signal traveling at the speed of light could carry information from one side of the experiment to the other, in time to coordinate the answers. The image is quiet, but profound. Two photons move away from their birthplace. Each heads toward a detector. While they are still traveling, the experiment shifts the question being asked. The choice is made so late that ordinary communication cannot explain the final pattern. If the correlations still cross Bell's line, the old whispering explanation becomes much harder to keep. Aspect's experiments did just that. The settings changed rapidly. The photons were measured. The results were gathered. And once again, the correlations crossed Bell's boundary. The particles continued to behave as quantum physics predicted, even when the questions were changed in flight, even when ordinary signals had no time to explain the agreement. The universe gave the same quiet answer. Not local realism, not hidden instructions in the simple Einsteinian sense. Something stranger, something that seemed to live below the surface of separateness. This does not mean that we can send messages faster than light. That is a common misunderstanding. Entanglement creates correlations, but it does not give us control over individual outcomes. Each local result still appears random. No one can choose the answer their particle gives. No one can use the connection to send a sentence across space. The speed limit of usable information remains protected. In that sense, Einstein's cosmic speed limit still stands. But the deeper idea of locality, the idea that distant systems must be completely independent unless something travels between them, is no longer so simple. Entangled particles are not useful as a faster-than-light telephone. They are more subtle than that. They show that nature can contain relationships that do not fit the ordinary picture of separate objects carrying separate facts. The connection is real in the mathematics. It is real in the experiments. But it is not a signal we can command. It is more like a shared structure, a quiet wholeness, a pattern that appears only when the two sides are later brought together and compared. This is part of what makes the discovery so fascinating. The universe allows a kind of connection that seems to ignore distance. And yet it prevents us from turning that connection into a message that outruns light. It opens one door while keeping another closed. It lets reality be stranger than locality, but not chaotic. There is still order. There is still structure. There are still rules. They are simply not the rules our everyday experience would have guessed. After Clauser and Aspect, the old debate had changed forever. It was no longer enough to say that hidden variables felt reasonable. It was no longer enough to say that particles might be carrying secret instructions. Any such picture would have to explain why experiment after experiment crossed Bell's line. Any deeper theory would have to preserve the successful predictions of quantum mechanics, while accepting that the simple version of local realism had failed. The calm surface of the world remained. The moon still crossed the sky. Chairs still held their shape. The earth still moved around the sun. Life still unfolded in the familiar language of objects and places. But beneath that surface, the laboratory had revealed something more delicate. The smallest parts of nature did not seem to be tiny independent things with complete private stories. At least in entangled systems, their story belonged to the pair, to the relationship, to a state that space alone could not divide. And that leads us to an even more fascinating question. If Clauser showed that the line could be crossed, and Aspect showed that the result could survive sharper timing, how far could scientists push the test? Could they remove still more possible loopholes? Could they choose measurement settings in a way that no hidden influence on Earth could easily predict? Could they use not only machines, but the universe itself, to decide how the particles would be asked their questions? The answer would carry the experiment far beyond the laboratory. It would reach outward to stars, then to quasars, to ancient light that began its journey long before human history. And in that next step, the story of entanglement becomes cosmic in the deepest sense, because the question of reality would no longer be asked only by instruments in a room. It would be asked with help from the sky itself. To ask the universe a question, sometimes a laboratory is not enough. Sometimes the question is so delicate that every small possibility must be considered. Every path by which the old explanation might escape must be examined. Every hidden door must be brought gently into the light. After Clauser and Aspect, the evidence had grown strong. Entangled particles crossed Bell's line. They did so again and again. They did so even when the measurement settings were changed quickly enough to make ordinary communication between the two sides deeply unlikely. But physics is careful. It does not only ask what appears to be true. In a Bell experiment, the measuring devices must choose what question to ask each particle. The setting on one side must be independent of the setting on the other, and both choices must be independent of the particles being measured. This sounds simple, but when physicists are testing the foundations of reality, even simple words become deep. What does it mean for a choice to be independent? What does it mean for a setting to be random? What if some hidden influence arranged both the particles and the measuring devices in advance? What if the apparent freedom of the experiment was not as free as it looked? This idea is difficult to take seriously in everyday life. It feels almost too strange. As if the universe were quietly scripting the experiment from the beginning, arranging the particles, the instruments, and the choices of the scientists so that the results would only appear quantum. Most physicists do not think this is a natural explanation. But the loophole is important because Bell tests depend on the independence of the choices. If the choices were somehow secretly connected to the particles from the start, then a hidden instruction universe might still imitate the quantum result. It would be a very unusual kind of hidden order, a kind of cosmic choreography. But science is patient with even unlikely possibilities. It tries to narrow them. It tries to push them back. It tries to make them so difficult that they no longer feel like reasonable explanations. And that is where the sky entered the experiment. If choices made by machines on Earth might, in principle, be questioned, then perhaps the choices could be handed to something older, something far away, something that began long before the laboratory was built, something that no ordinary influence in the experiment could easily control. Ancient starlight. The idea is beautiful. Let light from distant stars decide how the detectors will be set. Do not allow a person to choose. Do not rely only on a machine in the room. Instead, place telescopes under the night sky and let the color or arrival of starlight guide the measurement. A photon from a distant star begins its journey years, centuries, or even longer before the experiment. It crosses empty space. It passes through the quiet dark between worlds. It enters a telescope at the very moment the experiment needs a choice. And its properties help decide which question is asked of an entangled particle in the laboratory. In this way, the experiment reaches beyond the room, beyond the campus, beyond the Earth. It invites the universe itself to help choose the questions. There is something deeply calming about this image, a small laboratory on Earth. A pair of entangled particles moving toward detectors, and above it, starlight that began its journey long before the scientists were born, arriving just in time to take part in a test of reality. It is as though the night sky becomes a witness. Not a dramatic witness, not a voice, not a sign, but a source of old, distant events that can help protect the experiment from local influence. The choices are pushed farther into the past. The possible hidden coordination would have to reach farther and farther back. It would have to include not only the laboratory, but the stars themselves. And the farther back the source of the choice lies, the less reasonable the loophole becomes. Yet this is only part of the story. Because even stars, beautiful as they are not the oldest lights we can use. If scientists wanted to push the freedom of choice loophole even further back, they could look deeper into space. They could turn to objects whose light has traveled not for centuries, but for billions of years. Quasars. At the centers of young galaxies, enormous black holes feed on gas and dust. As matter spirals inward, it heats and shines with almost unimaginable brightness. A quasar can outshine the entire galaxy around it. Its light can cross vast reaches of cosmic history. When we see a distant quasar, we are not seeing the universe as it is now. We are seeing an ancient message. Light that may have left its source before the sun existed, before Earth formed, before oceans, continents, forests, or eyes. To use quasar light in a Bell experiment is to let the deep past participate in a present measurement. It is to allow events from billions of years ago, on opposite sides of the sky, to help decide how particles in a laboratory will be measured. The scale is almost impossible to hold in the mind. A photon, from an entangled pair, is born in a human instrument on Earth. At nearly the same time, light from a quasar, born when the universe was much younger, arrives at a telescope. That ancient quasar light helps determine the measurement setting. Then the detector records the answer. Later, the results are compared. And still, the correlations cross Bell's line. Still, the entangled particles behave as quantum physics predicts. Still, the ordinary local hidden instruction picture does not return. This does not prove that every imaginable loophole has been removed from the universe. Science rarely speaks in that kind of absolute language, but it pushes the old escape routes into stranger and stranger territory. To preserve a simple local realist picture after such tests, one would have to imagine a hidden coordination reaching across enormous distances and deep into cosmic time. One would have to imagine the particles, the detectors, the scientists, the stars, and the quasars all woven into a script arranged long before the experiment began. For most scientists, this is not a satisfying rescue. It gives up too much. It asks us to save an ordinary picture of particles by making the entire universe strangely prearranged. And so, with each experiment, the old picture becomes less natural. Not because anyone wanted it to fail. Not because mystery is more attractive than clarity, but because nature kept answering in the same quiet way. The correlations remained stronger than local realism allowed. The line was crossed. Again. And again. And again. But there was another kind of loophole to face. The problem of missed particles. In the early experiments, detectors did not catch every photon. Some were lost. Some passed unnoticed. Some never became part of the final data. This raised a question. What if the detected particles were not a fair sample of all the particles? What if the ones that were missed would have changed the result? Again, this was not the most compelling explanation. But a careful experiment must not leave such questions open if it can close them. To close this door, scientists needed systems that could be held more reliably than fragile photons. They needed particles that would not simply vanish into the noise. In 2015, several groups performed experiments designed to close major loopholes at the same time. One famous approach used tiny defects in diamonds. Inside a diamond, an electron can be trapped and controlled. Unlike a photon flying through space, such an electron can be held in place. It can be prepared. It can be measured with greater reliability. In one experiment, two such systems were placed far apart, far enough that no signal traveling at light speed could pass between them during the crucial measurement window. The systems were entangled through a careful process involving light. The attempts were difficult. Many failed. Only rare successful events could be used. But each success mattered. Each one was like a small opening through which reality could answer. The experimenters gathered the results patiently. They protected the timing. They guarded the independence of the measurements. They reduced the chance that missed detections could explain the outcome. And when the results were finally compared with Bell's boundary, the answer remained the same. The line was crossed. Other experiments around that period, using different methods, found the same essential result. This was an important moment, not because mystery suddenly appeared. Mystery had been there for a long time, but because the most serious experimental escape routes had been narrowed together. The simple idea that particles carry local hidden instructions, enough to explain all the observed correlations, no longer fit the evidence. Reality had been asked in laboratories. It had been asked with fast-changing measurement settings. It had been asked with distant stations. It had been asked with ancient starlight. It had been asked with quasars. It had been asked with experiments designed to close the major loopholes at once. And the answer stayed remarkably consistent. The universe did not behave like a collection of separate objects carrying complete private facts in the way Einstein hoped. At the quantum level, something more relational was happening, something that did not fit neatly into the categories of ordinary experience. The phrase often used is that the universe is not locally real, but those words can sound colder than the idea deserves. They can sound like a slogan. They can sound more final than our understanding really is. It is better to approach them gently. Not locally real does not mean nothing exists. It does not mean the world is an illusion. It does not mean thought creates the moon. It does not mean human consciousness commands the stars. It means that the combined assumptions of locality and realism, in their simple classical form, cannot both describe the quantum world. If we try to keep both, the experiments refuse. If we insist that particles always carry definite properties before measurement, and that distant events can only be connected by signals moving through space, Bell's line tells us what patterns should be possible. Nature gives patterns beyond that, and so something in the old picture must be revised. Perhaps reality is not made of independent little pieces in the way we imagine. Perhaps properties are not always settled before interaction. Perhaps relationships are more fundamental than objects. Perhaps the universe, at its deepest level, is less like a box full of separate things, and more like a woven whole, where some threads cannot be understood in isolation. This is where the story becomes quiet again. Because after all the instruments, all the detectors, all the ancient light and careful timing, we return to the same night sky where we began. The moon still looks calm. The stars still appear distant. The darkness still feels wide and silent. Nothing in everyday life seems to flicker with quantum uncertainty. A chair remains a chair. A mountain remains a mountain. Your hand remains your hand. The world is reliable at the scale where we live. And yet beneath that reliability, the experiments suggest a deeper layer that is not built from the same intuitions. The familiar world is not false. It is emergent. It is the large, steady surface of something more subtle. A surface where countless interactions smooth the quantum strangeness into the stable reality we can walk through, breathe in, and call home. But the universe has another surprise waiting. Because once we say that reality is not locally real in the simple classical sense, we must be careful. Very careful. We must not rush into fantasy. We must not turn quantum physics into magic. We must not say that consciousness creates everything, or that entanglement lets us send messages across the galaxy instantly. The truth is quieter than that, and in some ways, more beautiful. The final question is not whether the universe is broken. It is whether our old picture was ever large enough. To see that clearly, we must now step back from the experiments. We must gather the meaning of what they showed. We must ask what remains of Einstein's world, what quantum physics actually says, and what it might mean to live in a universe where separateness is not the final word. What remains, after all of this, is not a universe that has become less real. It is a universe that has become more subtle. The moon is still there in the night sky. The stars still burn in distant darkness. The earth still turns beneath us with a steadiness older than memory. Nothing in this story asks us to abandon the world we live in. It asks us to look beneath it. It asks us to understand that the reality we experience is not the deepest layer. It is the surface where deeper rules have become calm enough for life. When physicists say the universe is not locally real, they are not saying that nothing exists. They are not saying the world is a dream. They are not saying that the moon waits for a human mind before it becomes the moon. Those are easy misunderstandings. They are tempting because they sound poetic, but they are not what the experiments show. The experiments show something more precise, and in its own way, more beautiful. They show that the old classical picture cannot be kept whole. The idea that particles always carry definite properties before measurement, and the idea that distant things can only be connected by influences traveling through space. Both of these ideas feel natural. Both of them work beautifully in the world of ordinary objects. But when they are combined and taken down into the quantum world, the experiments refuse to obey them together. Bell drew the boundary. Clauser crossed it. Aspect tightened the question. Later experiments closed the doors through which the old explanation might escape. And in 2022, the Nobel Prize in Physics honored John Clauser, Alain Aspect, and Anton Zeilinger for helping turn one of the deepest questions about reality into something nature could answer. Their work did not make the universe stranger. The universe was already strange. Their work simply gave the strangeness a voice, a careful voice, a measured voice, a voice made of photons, detectors, correlations, and time. It told us that entangled particles cannot be understood as ordinary separate objects carrying ordinary pre-written answers. At least not if those answers must remain local in Einstein's sense. Something in our old picture must give way. Perhaps properties are not fully settled before measurement. Perhaps distant quantum systems are not fully separate in the way space makes them appear. Perhaps the deepest layer of reality is not made first of objects, but of relationships. This thought can feel disorienting at first. We are used to thinking of the universe as a collection of things. A planet here, a star there, a particle in one place, another particle in another place. Distance seems to divide them. Space seems to draw boundaries. And at the human scale, this picture is useful. It is how we move through the world. It is how we build houses, launch spacecraft, measure planets, and name the constellations. But the quantum world whispers that separateness may not be the final language of nature. Two particles can be far apart and still belong to one shared description. Their individual answers may not be fully meaningful until they are measured. Their connection may not be a message traveling through space. It may be something built into the whole system before we try to divide it into parts. This is why the result feels so deep. It does not merely add one strange fact to the edge of science. It changes the background against which all facts appear. It tells us that the universe is not always made of small independent pieces with private histories. Sometimes the relationship is the thing. Sometimes the whole is more fundamental than the parts we imagine inside it. And yet, the universe protects its calm. Entanglement does not allow us to send a message faster than light. No one can use it to speak instantly to a starship. No one can choose the result of a single quantum measurement and turn it into a signal. Each local outcome still arrives with randomness. Only later, when the two sides are compared through ordinary communication, does the hidden pattern appear. This is one of the quietest and most elegant balances in physics. The universe allows deep connection, but it does not allow controllable, faster-than-light communication. It loosens our picture of separateness, but it preserves the order of cause and effect. It lets the world be more connected than Einstein wanted, but not so wild that everything becomes chaos. In this way, Einstein was not simply defeated. He was partly preserved. His speed limit still stands. His curved space-time still guides planets, stars, galaxies, and light. His vision remains one of the great pillars of human understanding. But on the question that troubled him most, the question of whether reality could be both local and definite in the old way, nature gave an answer he did not expect. The world is not locally real in the simple classical sense. That sentence is small, but behind it is nearly a century of thought. Behind it are debates between Einstein and Bohr. Behind it is John Bell, quietly turning philosophy into mathematics. Behind it are laboratories where faint light was counted with extraordinary care. Behind it are stars and quasars, whose ancient photons helped choose how experiments would be performed. Behind it are decades of human patience, not panic, not fear, patience. The patience to let the universe speak in its own language. And perhaps this is the most important lesson of the story. Reality is not obligated to match the shape of our intuition. Our intuition was formed here, on a warm planet, among stones, water, trees, and bodies. It was shaped by things large enough to touch and slow enough to follow. It was never designed to understand photons. It was never designed to imagine a particle that has no definite answer before measurement. It was never designed to picture two distant systems described by one shared state. So when the quantum world feels strange, that does not mean the universe is broken. It may only mean that our minds are meeting a level of reality for which they were not originally made, and that is not frightening. It is humbling. It is even peaceful, because the familiar world still rises from the deeper one. The quantum fog does not prevent mountains from standing. It does not prevent oceans from moving under moonlight. It does not prevent stars from forming in cold clouds of gas. It does not prevent you from resting here, listening, breathing, and belonging to the same universe these experiments reveal. Somehow, from countless uncertain interactions, a stable world appears. From particles that do not always carry definite properties, matter becomes reliable. From relationships too deep for ordinary separateness, galaxies form, planets cool, and life becomes possible. The chair beneath you feels solid. The floor remains steady. The moon keeps its path across the night. The everyday world is not an illusion. It is an emergence, a calm pattern rising from a deeper ocean of possibility. This is where the story becomes less about physics alone and more about perspective. For centuries, science has shown us that we are not at the center. Earth is not the center of the solar system. The sun is not the center of the galaxy. The Milky Way is one galaxy among billions. And now, quantum physics asks us to loosen another center. The center of common sense. The belief that reality must be built in the same way ordinary experience presents it to us. The universe is not required to be intuitive. It is only required to be itself. And the more carefully we listen, the more delicate it becomes. At the surface, it is calm enough for rivers, forests, cities, and sleep. At the depths, it is woven from probabilities, interactions, and relationships that seem to stretch beyond the boundaries of ordinary space. Both are true. The surface and the depth. The solid and the subtle. The moon in the sky and the quantum uncertainty in the particles that make it. We do not have to choose between wonder and reality. The wonder is part of reality. Einstein once hoped that a deeper theory would restore a world of clear hidden facts. Perhaps one day, physics will go deeper still. Perhaps quantum mechanics is not the final language. Perhaps beneath it there is another structure we have not yet learned how to hear. Science remains open because the universe remains larger than every theory we build around it. But whatever comes next must carry the lesson of Bell's line. It must explain why nature crosses the boundary that local realism cannot cross. It must explain why entangled systems behave as though the old separations are not enough. It must explain why the world we touch is steady, while the world beneath it is so quietly strange. And maybe that is the most beautiful place to end, not with certainty closing the door, but with understanding opening it a little wider. The universe is not wrong. Our first picture was incomplete. We imagined reality as a collection of separate things, each carrying its own private facts, each waiting quietly in space. But the deeper world seems to speak in another grammar, a grammar of connection, a grammar of possibility, a grammar in which measurement is not just discovery, but participation. Not participation by human thought alone, not magic, not consciousness commanding matter, but physical interaction, contact, relationship, the universe meeting itself again and again, and becoming definite in the process. When you look at the night sky now, nothing has to appear different. The stars do not need to flicker strangely. The moon does not need to tremble. The darkness does not need to reveal its hidden machinery. It can remain quiet. That quietness is part of its beauty. But somewhere beneath the stillness, the lesson remains. Reality is deeper than appearance. Distance is not always the kind of separation we imagined. And the universe we belong to is woven more finely than common sense can see. So let the thought settle gently. Every atom in your body belongs to this same strange world. Every breath is part of a cosmos whose deepest rules are still unfolding before us. The same reality that bends starlight around galaxies also lets particles share a state across distance. The same universe that builds moons and mountains also holds possibilities until interaction draws them into form. You are not outside that mystery. You are made of it. You are resting inside it. And as the night deepens, the cosmos continues in silence. Stars burn. Light travels. Particles meet and separate. Galaxies turn slowly in the dark. And beneath it all, reality remains what it has always been. Not simple, not ordinary, not fully captured by the first picture we made of it, but patient, coherent, vast, and quietly more connected than we ever imagined.